Over the last two videos, we have examined the classification and properties of matter as well as changes that matter goes through. Today we're going to look at one of the items in the classification, and that is the element. An element being a pure substance, and this type of pure substance is made up of one type of particle, and those particles we call atoms. So today we're going to look at some vocabulary as well as some terminology and ways of doing calculations surrounding atoms. So atoms are made of parts. Okay? So some of the original definitions of atoms had them as being indivisible particles that were made up of nothing smaller, so they were considered the smallest particles. We now know that atoms are made up of smaller parts, including protons, neutrons, and electrons. We're going to spend some time looking at some of the properties of these three subatomic particles. Now, the term subatomic particle means smaller than an atom. So these are within atoms. The first of those is the proton. And protons have a very low mass, a mass of 1.67 times 10 to the negative 27th kilograms. So very, very small. They have a charge of positive 1, and we don't put a unit on this because it's a relative charge, meaning that it's positive 1 compared to some other particle within the atom. And it's located in a part of the atom known as the nucleus. The nucleus is the center of the atom. So this nucleus contains all of the positive particles in the atom. So when we look at a diagram of an atom, this being a solar system type model of the atom, we have a nucleus here in the center, represented by this, and then we have pathways or orbits around the outside of this nucleus. Here we have 6 protons, although you can't see all 6. They're the ones that are labeled positive, and they're located in the center with these negative particles out here going around them in some sort of pathway. The number of protons in an element is the atomic number. So the atomic number is the number of protons in an atomic nucleus, and most importantly, it is constant for any given element. If atomic number changes, we actually change the identity of the element itself. So hydrogen, for instance, is 1 for an atomic number. If we have atomic number 2, that would be helium. So when we look at the periodic table, we can see that atomic number is actually one of the values given on any periodic table, and it is always a whole number. So that's important because you sometimes have to choose between numbers. And it generally is represented, could be in different locations, but often it is like this. Hydrogen is 1, helium 2, lithium 3, and so forth, or lead 82 right here, directly above the periodic table. But when you look, you may find them in the top left corner. You might find them bottom left. They can be all sorts of places, but you look for that whole number. You can also tell which one it is because the elements on the table are actually arranged in that order. So we have element 1, 2, 3, 4, 5, 6, 7, 8, and so forth, down to 118 down here. Next subatomic particle is the neutron. Neutron has a mass that to the second decimal place is identical to that of a proton. If you go out more decimal places, it's actually slightly more massive. It has a charge, as the name neutron implies, that is neutral, so it has no charge. And its location is also in the nucleus. So the nucleus shares, is made up of 2 particles, the protons and the neutrons. And actually we have a term called nucleon, and that's any particle in the nucleus. That would be protons and neutrons. A number that we use to describe the number of neutrons is called the mass number. Mass number is a sum, and it's simply the sum of the nucleons, or the sum of the protons and the neutrons inside the nucleus. So we can get the number of neutrons if we know the mass number and the atomic number, because mass number minus atomic number equals the number of neutrons. Mass number minus atomic number equals neutrons. Mass numbers are variable. So while a given element is always going to have a constant atomic number, mass number can change. And that's due to the potential to have different numbers of neutrons. Every atom of an element does not have the same number of neutrons. We call those different types of atoms of the same element isotopes. Isotopes are atoms of the same element with different numbers of neutrons. And if it's the same element, it means the same atomic number or the same number of protons, but their number of neutrons can change. Since protons and neutrons have mass, then we would say that if they have different numbers of neutrons, then those atoms would have different masses. So we have different numbers of neutrons. We could also say different mass numbers. So to be able to represent atoms of different elements, we're going to use a certain type of notation known as an isotope notation. Isotope notation can be in two common forms. One of those is the superscript-subscript notation. So in superscript-subscript, if we have, as an example, the element X, we're going to represent as a superscript. We'll have a superscript here, and we'll have a subscript there to the left of the symbol. A is equal to the mass number, whereas Z is equal to the atomic number. And X is just the element symbol. So when we look at the superscript-subscript notation for a type of carbon, we have carbon with an atomic number of 6 and a mass number of 14. So if we wanted to find the number of neutrons with this, neutrons equal the mass number A minus the atomic number Z. This is A, this is Z. So we would have 14 minus 6, which is going to be 8. And you can see here we have at least 3 different forms of carbon. Carbon with a mass number of 12, with a mass number of 13, and with a mass number of 14. But you can also see that we have, in all of them, we have an atomic number of 6, which means that carbon has 6 protons. Now, besides the superscript-subscript notation, we also have what we call hyphen notation, often used in biology, but often used just in speech also. And in hyphen notation, we're going to take this form, the element symbol, and then a hyphen. This is not a minus, this is a hyphen, and then mass number. So we have something like this. Carbon 12, or C with a mass number of 12, could be written as just C12. And we would actually say it probably the way this is written. We would call this carbon 12 if we were saying it orally. If you were writing it, you would just write C12, or you would write this symbol. An important note about chemical behavior, chemical properties. Isotopes of an element all act the same chemically, so they have the same chemical properties. So if we take hydrogen and oxygen and make water, we may not have all the same exact same molecules of water in the end, because there could be different isotopes of both hydrogen and oxygen present in the water, but they would combine in exactly the same way, making H2O. So, as some example problems, what is the symbol for a nucleus which contains 19 protons and 20 neutrons? Okay, so we're going to use, to begin with, we're going to use the symbol X for this, and we can identify it later. It has 19 protons, so 19 protons means that its atomic number, Z, is equal to 19, and its mass number is going to be the sum of, change that to what it's supposed to be, its mass number A is going to be the sum of the number of protons, 19, plus the number of neutrons, 20, and that's going to be equal to 39. So the way we would put this in the symbol is that we would have X, the mass number of 39, and an atomic number of 19. Okay. Another example, what's the symbol for a nucleus which contains 8 protons and 8 neutrons? So we have 8 protons, that means atomic number equals 8, and mass number equals, let me put this symbol in, 8p plus. We'll let p plus stand for protons, and n0 stand for neutrons. So we've got 8p plus plus 8 neutrons. That's going to be a total of 16 particles. Okay, so our symbol would be X. We don't necessarily know what this symbol is, but it would be X with mass number of 16 and atomic number of 8. And we can identify this element just by looking at the atomic number. Atomic number 8 is oxygen. And if we went to the previous slide, the atomic number 19 is potassium. So this would be K, potassium 39, an atomic number of 19. And this one would be oxygen 16, which is the most common form of oxygen, O16 over 8. Third subatomic particle is the electron, which has a tiny mass compared to the others, only 9.11 times 10 to the negative 31st kilograms. Remember, the other two had exponents of negative 27, which is significantly larger than 10 to the negative 31st. The charge is negative 1. It's exactly the opposite in charge of a proton. And its location is outside the nucleus. And in a region that we're just going to call the electron cloud for now. So it's in a region separated from the nucleus. Now, in a neutral atom, in fact, most matter in the world is neutral. But we know that it's made up of individual particles that have charge, positive protons and negative electrons. So since they're neutral, the number of negative charges and the number of positive charges have to be equivalent. So number of electrons equals the number of protons if we have a neutral atom. However, we don't have to have neutral atoms. We can have something known as an ion, which is a charged atom. So we have atoms and we have ions. Ions always result from gains or losses in electrons. Neutrons and protons generally stay put in the atomic nucleus, and they're held very strongly in place, but electrons can sometimes move from place to place. If we have a loss of electrons, fewer electrons than protons, we have what's known as a cation. Cation is positively charged and it results from losses of electrons, and for each electron lost, the ion becomes more positive. So if we have 8 protons in the nucleus and we have 8 electrons out in a ring somewhere, then we would say that we have 8 positives, 8 negatives, so this would be neutral. However, if this atom loses some electrons, if it loses one electron, giving us 8 protons compared to lose 6 electrons, then we have 2 more positives than we have negatives. So this would be 8 positives, or we could say positive 8 plus a negative 6 equals a positive 2. So the overall charge of this cation would be positive 2. Anions, on the other hand, are negatively charged, so negative ions. They result from gaining electrons. When you gain electrons and electrons are negatively charged, then the end result is that we're going to be negative overall. So for instance, if we had, let's say, 9 protons, and we had a couple of rings of electrons, maybe we've got 2 electrons here, and then in another ring we've got 7 electrons. Then right now we've got 9 positives and 9 total negatives. This would be neutral. However, if we add an electron to this ring to give 8 electrons, we now have 10 electrons, 10 electrons and 9 protons. So this is positive 9 plus a negative 10, that equals negative 1. So this would be an anion with a negative 1 charge. So let's do a couple of sample problems. Sample problem number 1, we've got an isotope of an element that has the following symbol. We want to find the following information: the number of protons, the number of neutrons, the number of electrons, and we also want to try to identify this element. So first of all, from the symbol right here, we can get the number of protons pretty quickly. That's 92. Because the bottom number in this representation, the bottom number is going to be the atomic number. To get the number of electrons, we can assume that the atom's neutral unless we're told that it has a specific charge. So our number of electrons has to be the same as the number of protons. And then to get the number of neutrons, that's going to be the number of protons, which is the atomic number, the number of protons and neutrons combined, which is the mass number, minus the atomic number, the number of protons. So that's going to be 238, because this is the mass number, minus the atomic number, 92. Now we could also look at it like this, just to give you another view of it. If we have x, 238, and 92, and really all we have to do is subtract 238 minus 92. In either case, we're going to get 146. So the number of neutrons, 146, protons and electrons, 92. Another example. Certain isotope of an element. Oh, we need to find out what that was as well. I didn't identify it. To identify, look at the atomic number and find that element on your periodic table. This is uranium. Okay. So with this one, we've got an isotope of an element that has a mass number of 24. So A equals 24. And an atomic number, Z, equal to 11. We want to find number of protons, number of neutrons, number of electrons. And we also want to identify the element. Okay, so I'll just put a question mark for what is the element. Okay, number of protons is the atomic number, so this is 11. The number of electrons is the same as the atomic number, 11, assuming that we're neutral. The number of neutrons is going to be the atomic number minus, the mass number minus the atomic number. So this is going to be 24 minus 11. And 24 minus 11 is 13. And our identity of the element, we look at the atomic number 11, find that on the periodic table, and that is going to be sodium. So the best symbol for this would be Na, and 24 and 11. Okay, sample problem 3. A neutral atom of an isotope of a specific element has 7 electrons and a mass number of 15. Find the following. We want to know the number of protons, number of neutrons, number of electrons, and what is it? What's the identity? All right. First of all, we know that we have 7 electrons. We have a neutral atom according to the problem, so that means the number of protons is the same. We know that the mass number is 15, so the number of neutrons has to be 8. And the identity of this element, element with an atomic number of 7, would be nitrogen. Okay, let's do one with an ion. We have an ion has a charge of positive 1. Okay, so we've got some sort of, we'll just call it X, and it's got a positive 1 charge. We put charges as superscripts on the right side of the symbol. It has 18 electrons. Mass number is 38. Put that up there. We want to find the atomic number, which is here. The number of protons, which is the same, the number of neutrons, and the identity of what the ion is. Okay, well, first of all, it has a charge of positive 1. Okay, we know that we have 18 electrons. So if we have 18 electrons, that's 18 or negative 18 plus the number of protons, we'll call that X, equals positive 1. If you solve this, add 18 to either side, X is equal to 19. So this is the total charge. We can actually write an equation for this. Total charge equals number of, or I should say total charge equals, erase, oops, total charge equals total positive plus total negative charge. Total positive is going to be the same as number of protons. Total negative is the same as number of electrons, but it's going to be a negative, and that gives us our total charge. Okay, so we had total charge is positive 1, number of protons we're going to call X because we didn't know it, plus a negative 18 would be our charge of all our 18 electrons, so that means X is going to be equal to 19. So we've got the symbol X. It has a mass number of 38. It has an atomic number of protons, as 19, and it's got a positive 1 charge. We would call this the potassium ion. Not just potassium, but the potassium ion. It's potassium because the ion has the same atomic number as the element that it came from.